right, guys, good morning. So this is week 11, so we've got one more week to go. So today I'm going to go through just one video. I hope you guys watch this video. This video is on some examples on one sample test. All right, announcement number one. If you haven't done it, could you please just submit the answer to quiz 10 before 11 a.m. today. As usual, I will send you the correct answer and the details of derivation later today. And also let me remind you, the ARC coursework, which is here, is due next Friday by 11 a.m., right? So if you haven't done it, or if you haven't submitted it, please do so by 11 a.m. Friday next week. And I will return the ARC coursework to you within a few days, certainly before the exam. The exam, by the way, is on the 25th of May, which is a Wednesday. So you will get an email from me giving the mark for the ARC coursework certainly before next Wednesday, the 25th of May. And as I said before, I do all the marking myself. So I will mark all of your ARC coursework by myself. And I will send you your mark and also the feedback and also a copy of your ARC coursework with annotation on it, right? Okay. Okay. So you will get that certainly before the exam date. Right. The next week is basically a revision week, right? So next Friday, which is the 20th, I will go through some problems and that may help you to perform well in the exam, right? So if you have any questions that you'd like me to go through Friday next week, please email them to me, right? So please, without your questions, I will not be able to run the revision session on Friday next week, okay? And coming back to this week, there were 6 tutorials this week, and these are the videos. Hello. These are the 6 videos on the 6 tutorials that took place this week. The attendance was very poor. Like, I think in one session there were only 3 students attending the tutorial in one of the sessions. I don't know what's up with you guys, but anyway, if you haven't been to the tutorials, please watch these videos. And there's also a video, this one here, which gives the full solutions to all the problems. So it gives you full video solutions for all the 7 questions on the sheet, right? All right, guys, and there's also a typed solution, which is this one. And there's also handwritten solutions to all the questions, which is this one, right? All right, so please try to read or watch all of those stuff when you have time. All right, so now let me go through the video for this week, which you haven't been. So basically, this is the one. This is I think I did, let me see how many examples I did. I did 9 examples. 9 examples on one sample test. So this is the first example I did, where you have a random sample from normal and sigma squared is known. We are testing this versus this. And this is the rejection rule, and the question was to find beta. Were you okay with this example or not? I mean, were you okay? Anybody who was not okay with this example, number 1? Example 2. The rejection, the same as example 1, but the rejection rule is this one. The question is to find beta. Were you okay with this? Anybody who wasn't okay with this? Example 3, the same as example 1, but the rejection rule is this one. Find beta. Were you okay with this? Come on, guys, talk to me. Yeah? Example 4 was this one. You have a bag contains 20 balls. P is the probability that a ball is defective. Y is the number of defective balls. And you're testing this versus this, P equal to 0.2 versus P not equal to 0.2. And we reject H0 if Y is greater than or equal to 7 or less than or equal to 1. Find beta. Are you okay with this? No? Example number 4. You have problems? No? Example number 5 was this, where you have IID from normal with mean mu variance for testing this versus this, and this is the rejection rule, find beta. So this is the solution for it. Are you guys okay with this? Just, feel free to say no if you are not okay. Okay? And this is example 6. So you have a random sample from normal with mean mu and variance 20, testing this versus this. So the question is, how large should n be, right? If we require that the probability that at least 0.9, the standard test will reject H0 when in fact the true value is mu equal to 95, right? How large should n be? So, were you guys okay with this example, or you want me to go through? Example 6, you okay? Come on, guys, talk to me. This is example 7. Consider testing this versus this, find beta. Yeah, so this is based on the chi-squared statistic. And this is example 8. So you have a geometric random variable. You're testing for p equal to 0.2 versus p equal to 0.1 versus 0.2. Reject if x is less than or equal to 5. Find alpha and beta. This is the solution. You guys okay? Are you okay with this? And finally, this was example 9. Some people ask me some questions. Well, there is the last equation is not correct. Well, it's correct except for n squared should be n. I think some of you noted that. Instead of n squared, you should have n here. So I'm sorry about this, right? So in the left-hand side of the last equation, n squared should be n, right? Except for that, the solution is correct, right? Were you guys okay with this? All right, all right. So if you're not okay, just feel free to say no or see me after the session today, right? All right, so what I'm going to do now is to go through some more examples, right? And try to see. As I said before, there will be question on one sample test, but two sample test or two sample confidence interval will not come in the exam. I know some of you have been emailing me asking what will come in the exam. What I can tell you that the two sample confidence interval and the two sample test of hypothesis will not be examinable, right? Okay? All right. So example 10. right? All right, so here you have a random sample from a normal with mean mu and variance equal to 1, testing this versus this, and this is the rule for rejection, and we want to find alpha and beta. Remember, alpha is the probability of type 1 error, which is the probability of rejecting the null hypothesis when it is true, which is mu equal to 0, right? So there's a probability that x bar is greater than k given that mu is equal to 0, right? Now I'm going to do standardization. You'll see in a minute why I'm doing this. Well, okay. Now, you should look at this guy here. You should know, like, okay, let me show you where this comes from. You should go to the normal distribution, which we talked about a long time ago, right? And one of the properties that I talked about is the following, is the property number 6, right? If you look at property number 6, it says that the sample mean from a normal distribution has also a normal distribution with parameters mu and sigma squared by n, right? So that's the property I'm using. So using property 6, from the normal distribution, right? You can see that this guy here, conditional on the population mean being equal to 0. This is standard normal greater than, this simplifies to root of n times k. Okay. Now I have removed the conditioning here because we have already used the conditioning to argue that this has the standard normal, right? Okay, so alpha is equal to 1 minus phi of root of n times k. Okay, is that clear to all of you or not? Any questions, guys? Please give a shout. Okay. Right. Beta is the probability of type 2 error. Oh, sorry. Beta is the probability of type 2 error, right? Which is defined as you know from the review session last week. You should know the type 2 error occurs when you accept the null hypothesis when it's not true, right? So you accept H0 when it is not true, which means that mu must be equal to 1. Yeah? Okay? Now, we know that the accepting H0 is the opposite of rejecting, and we know from above that this is the rule for rejecting the null hypothesis, right? So the rule for accepting the null hypothesis must be the sample mean being less than or equal to k, given that mu equals to 1. Right? Okay. Now, I'm going to do the same thing I did in the first part, right? So I'm going to standardize this, but this time, because the population mean is equal to 1, I need to subtract 1, not 0, right? Because we are conditioning on mu being equal to 1, right? So we subtract 1 and divide by 1 over root of n. Okay. Now, again, by property 6 on the screen, this guy here has this standard normal distribution, right? So what you have is the probability that n01 is less than or equal to root of n times k minus 1. Again, we no longer need the conditioning because the conditioning has been used to argue that this has the standard normal, right? So the final answer is phi or phi okay. Is that clear to all of you or no? Come on, guys, give me You okay, no? Are you okay, guys? Yes, no? Yeah? All right. So this is example number 10. Now go to the next example. Example 11. Okay. So it's similar to the previous example, except the rejection rule is now involves the absolute sign. So you have to be a little careful when the rejection rule involves the absolute sign, right? Okay, so let's see how we can find alpha. So this is the probability of rejecting H0 when mu is equal to 0, right? So this is the probability that the absolute value of x bar is greater than k, given mu is 0. Now, I'm sure you should know all your math better than I do, but you know that if the absolute value of something is greater than a constant, it means two things. It means either without the absolute value, either x bar is greater than k, or x bar is less than minus of k. I'm sure you guys know this, right, from your math background, okay? Yeah? Now these two events are mutually exclusive, that meaning that they cannot occur at the same time, right? So therefore their union is the you can write them as the sum of the probabilities. Okay? Are you get with me? Right? All right. And now what I'm going to do in the remaining is just to apply the standardization I did in the previous example. So to standardize, I'm going to subtract the mean and divide by 1 sigma divided by root of n. You see what I'm doing? Okay. All right. Okay. Now, this guy here, because of property 6, because of property number 6 of the normal distribution, this must have standard. This guy here and these two guys should have standard normal distributions, right? Okay. So you have the probability that NO1 greater than root of n times k plus the probability that N01 less than minus root of n times k. Okay, once again, I remove the conditioning because we have used the conditioning to argue that these two guys have the standard normal, right, because of property number 6, right? Right, so this becomes 1 minus this guy here, you can write it as yeah. Okay. So this is 1 minus phi of root of n times k plus phi times root of n times k. Right? Are you guys with me or what? Yeah? Any questions on this, guys? You're right? Okay. So that's your alpha. Now to find beta, you do the same thing or similar. So let me try to show you now. To find beta, which is the probability of accepting the null hypothesis when it is not true, which is meaning here, in this case, it means mu not equal to 0, right? All right, so this is the rule for rejecting, right? So the rule for accepting would be the probability that x bar is less than or equal to k, given mu is not equal to 0. Now, once again, from your math background, you should know that if an absolute value of something is less or equal to a constant, that means without the absolute value, it will be between minus k and plus k, right? You know this, right? Yeah, okay. Anyway, so the next thing I'm going to do is standardize things. So I'm going to subtract. Now, in this case, the population mean is not 0, is a constant which is not equal to 0. So what you need to do, you need to subtract mu, right? And then divide by all right. Now, because of property number 6, the thing in the middle has a standard normal distribution, right? So what you have is root of n times k plus mu again. I remove the conditioning because we don't need the conditioning once it has been used, right? Okay, so this will become, you can write this as phi or phi at root of n times k minus mu, take away phi at minus root of n times k plus mu. So this is the expression for the type 2 error probability. Is that okay with you guys, all of you, or not? Yeah? Yes? No? All right. So that we have done 2 examples so far. The third example is going to be different. So this is example 12. Now, S squared here is the sample variance. I'm sure you know what a sample variance is, right? Remember, when I say sample, I mean at the beginning, you may recall that in week 1 of this course, I gave you 2 definitions of sample variance, but the one you're going to use in the exam is going to be the one with the unbiased version, which is n1 divided by n minus 1, right? So you should always use the version which is unbiased for the sample variance, right? So when I say S squared or sample variance, I mean automatically the unbiased version, right? Which is 1 divided by n minus 1 times the sum of the squares of the deviations from the sample mean, right? Okay? Okay, let's see how we can do this. Right, so just to clarify, what I mean here is S squared, just to refresh your mind. This is what I mean when I say this is the formula for the sample variance that you will use for the exam if it comes, right? This is the formula that you will use, right? Okay. All right. So the probability alpha is the probability of rejecting H0 when sigma squared equals to 1. So that's the probability of S squared being greater than K when sigma squared is equal to 1. Right? So which is the probability that 1 over n minus 1 right? Now, what I'm going to do is I'm going to take the n minus 1 to the right-hand side of the inequality, right? So I'm going to take this guy here to the right-hand side. So this will become all right. Now let me ask you, let me go back to you should go back to the chi-square distribution. One of the properties I gave you is this one here. Do you remember this property here, property number 3, which says that if you have a random sample from a normal with 0 mean and variance sigma squared, right, then this guy here has a distribution which is sigma squared times chi squared n minus 1, right? So using the property 3, using property 3 from the notes on chi squared, right, you can see that this guy must have a chi-square distribution with n minus 1 degree of freedom, right? And sigma squared is 1, right? So 1 squared is 1, right? So once again, I'm removing the condition because conditional on this, conditional on sigma squared equal to 1, right? This guy has the chi-square distribution, right? Okay. So this you can write as 1 minus the probability that chi squared n minus 1 and this you can write as 1 minus f. So this is the notation I use for the CDF of a, excuse me. So this is this notation here. This notation here denotes the CDF of a chi-squared variable with n minus 1 degree of freedom. All right? Are you okay with this, guys? Yes? No? Right? Come on, guys. You were short. You should not clear. Okay? So this is your alpha. Now to find beta, so remember the beta is the probability of accepting the null hypothesis when it is not true. So in this case, is sigma squared not equal to 1. Right? All right. Now we know the probability. Sorry, the rejection rule. The rejection rule is sigma s squared greater than k. Right. So the acceptance rule. The acceptance rule will be s squared less than or equal to k. Right. Okay. All right. So once again, what I'm going to do is I'm going to take this guy here to the right-hand side of the inequality. So you get the probability Okay, in the next step, I'm going to use property 3. According to property 3, this conditional on sigma squared not equal to 1, right? This must have yeah? You follow me? Yeah? It's according to property 3. So this you can write as the probability that a chi-squared variable with n minus 1 degree of freedom, you should take this to the right-hand side as less than or equal to n minus 1 times k divided by sigma squared. Yeah? So finally, you can write this as the CDF of a chi-squared variable at okay. So is this clear to all of you or not? Yeah? You guys okay? All right. I mean, don't be shy, guys. If it's not okay, just feel free to say so. Right. The next example is different too. So this is example 12. Next one is example 13. Right. This is a little different from the examples that we've done so far. I'll show you why. I'll show you why in a minute. So let's start with alpha. Right? Okay, now let me explain why it's different. Because if you look at the notes on student T distribution, which is this one, right? One of the properties I gave you is the following. I don't know whether you remember this or not. Property number 4. Do you guys remember this property? Which says that if you have a random sample from a normal with 0 mean and variance sigma squared, something of this form has a T distribution with n minus 1 degree of freedom, right? You remember this property, right? That's what I'm going to use. So I'm going to make the left-hand side, you need to make the left-hand side look like the left-hand side of star, equation star, right? So to do that, what you need to do is this. What you need to do is you need to make this, look like what is on the screen, right? So okay, right? Now using property 4, on the notes on students T, this guy here must have a T distribution with n minus 1 degree of freedom, right? So this is the probability that a T variable with n minus 1 degree of freedom is greater than root of n times k. And once again, we don't need the conditioning because we are using the conditioning to argue that this has the T with n minus 1 degree of freedom, right? Okay, now this you can write as 1 minus the probability that and this you can write as 1 minus the CDF of a T variable with n minus 1 degree of freedom at root of n times k. Okay. All right. Is that clear to all of you or no? Yeah. So, all right. So let me think. It's difficult to find beta, but it will be. You can find beta, but it'll be. Okay, let's see how we can find beta, but it will require some more math. So to find beta, you're gonna find the probability of accepting the null hypothesis when mu is, sorry, this should be 0, guys, not 1. Excuse me, this should be mu not equal to 0, okay, not 1. So this should be mu not equal to 0, right? Okay. Now accepting is the opposite of rejecting the null hypothesis. So this is the probability that x bar divided by s is less than or equal to k when mu is not equal to 0. Now the problem here is that you can't use this rule straight away because the property number 4 assumes that the mean is 0, right? You see what I'm saying? The property number 6 assumes that the population mean, is equal to 0. So we can't do what we did earlier, right? Okay. So to do this, you need to try some trick. I mean, you may find this a little bit difficult, but what you need to do is the following, right? Now, x bar, we know, is normal with mean not equal to 0, right? So to make that equal to 0, I'm going to subtract Can you see what I'm, okay. Now, x bar minus mu as a variable has mean equal to 0, right? Okay, now divide sorry, there should be a mu here. I left out. Okay, like this, right? Okay, now you should look at this guy here, right? This, right? According to property 4, must have a t distribution with n minus 1 degree of freedom, right? Okay, so what you can say, is this is the probability that a t variable with n minus 1 degree of freedom is less than equal to s k minus mu divided by s root n, right? And finally, this will be the CDF of a t variable with n minus 1 degree of freedom at sk minus mu divided by s by root of n. I know this is a little bit complicated, but I hope you get what I'm saying. I mean, I hope you. I will not ask you something like this in the exam, but I hope you understood what I meant, right? Because x bar has mean not equal to 0, you can't straight away use this property number 4, right? Because in order to use property 4, the mean must be 0, right? You follow me? So in order to use, so what I did is to subtract the population mean. Subtracting the population mean from x bar makes the mean go to 0, right? Okay, and then I divided both sides by s by root of n, right? And then after that you can use property 4. So in this step here, I have used property number 4. Right? Okay. Right. So I hope you get what I mean. Right. So I think we are nearly approaching the time, but I only have 2 minutes left. So what I'm going to do is I'm going to give you some homework, if that is okay. I mean, just to prepare you for the exam, which is not far. So let me give you a homework problem. Okay, this one. Homework problem is, suppose all right, this is the homework problem. It's similar to the previous example I did, except here we have the absolute sign. We have the absolute sign for the sample mean x bar, right? So you have to be a little careful. And here I only want you to work out alpha, not beta, because working out beta will be a little complicated in this example. As you saw in the last example, working out beta was a little bit more work. All right, so I only want you to work out alpha, the type 1 error probability. All right, guys, so just to remind you, the R coursework is due next Friday by 11 o'clock, right? When you submit your R coursework, please upload a PDF version, not doc. I don't like reading doc files, and I saw some of you have already uploaded doc files. which I really don't like. But anyway, I mean, I will accept them in any case. But if you haven't done if you have not uploaded it yet, please upload as a PDF file, not as doc, right? When you're using tech, you can easily create a PDF file. I mean, if you're using LaTeX. And also in MS Word, it's also easy to create a PDF version, right? So please upload the PDF version, all right? Okay, guys, have a good weekend. As usual, I will send you the solutions to quiz number 10 shortly after 11 o'clock, right?
I will re-upload my our coursework as a PDF file.
It's okay.
Because I uploaded it before as a Microsoft Word.
Yeah, no, it's all right. But yeah, like you can.
Well, as you said, as you've already said that, I will just re-upload it so that you could correct it, to see it
Okay.
easily.
Okay. All right, man. Thank you for that. How are you, sir?
Good. Today the coursework.
Yeah.
I've done it, but I don't know how to. Do I use LaTeX or better to upload my thing onto your Word?
Are you using LaTeX?
I'm not sure. I'm not sure which one to use.
It's up to you. You can use Word or LaTeX, but in either case, just use the PDF version. Get the PDF and upload it to upload to Blackboard, right?
Okay.
You know how? I mean, if you're using Word, it's easy to create the PDF version, right?
Okay. So Word is better than.
Well, both are good. I mean, both are good. I mean, either LaTeX or Word, both are good.
Ask a question.
Yeah.
From a hospital.
Yeah.
This one. I'm confused.
You're confused?
Yeah. So,
Which part?
part B. 这几年了。This one.
Part B. Yeah, sorry.
Yeah. Which week we have learned that?
We learned this on summary statistics. So you should look at summary statistics.
It's a week.
Yeah, I think it's week 2 or week 3. I can't remember.
Yes, sir. You just say the hyperbolic test and the interval are not examinable. Is it?
2 sample. Yeah, 2 sample test and 2 sample confidence intervals.
Apart from that, other
Yeah.
exam.
Yeah. Yeah. So I'm just using the formula. You know this formula here, this formula. I'm just using the formula. If you look at summary statistics, I don't have the notes here, but if you look at summary statistics, you will see what I'm using. You will see what I'm using. Yeah, I'm using. How do you click on this? Can you click on this? Yeah, go down. Can you go down? This one. I'm using this formula, guys, to do part B. Did you look at the solution? Did you look at the solution for this?
Yeah.
You didn't understand?
Yeah. Here's the solution.
Yeah, but I also have the solution. Hello. Nobody is here for you.
You mean answer sheet?
Yeah, the solution. You should go to the web.